So, today we will take the first steps towards solving Cauchy problems for quasi-linear equations. So, in this lecture we are going to look at the relation between characteristic curves and integral surfaces. The outline of the today's lecture is, first we discuss an idea to solve Cauchy problems for linear and semilinear equations, which are clearly the simplest form of the quasi-linear equations, special forms but simplest. So, we try to solve the Cauchy problem for linear and semilinear equations and we see whether we encounter any difficulties. If we encounter, we see how to overcome them, and when we generalize to quasi-linear, what should be done will also be discussed. And then we look at the relation between characteristic curves and integral surfaces for quasi-linear equations. This we are begged to look at this as a consequence of our analysis for the point 1. When we look at linear and semilinear equations and try to solve the Cauchy problem, naturally we are led to asking certain questions that will lead us to our understanding of this. It will lead us to inquire into the relation between characteristic curves and integral surfaces, which we will do more generally for the quasi-linear equations. So, first we discuss an idea to solve Cauchy problem for linear and semilinear equations. Let us recall from lecture 2.1, where we have introduced the notion of Cauchy problems and quasi-linear equations. So, this is the definition of the quasi-linear equation. It is an equation of the form A x y u ux plus B x y u y equal to C x y u. Any reasonable analysis of this can be done at an elementary level. For that, we need to assume that A, B, C are nice functions, that is C1 functions. They are functions of 3 variables. So, they are defined in a domain omega 3 in R3, and we want that A and B do not vanish simultaneously, that is A comma B is not equal to 0 0 at every point of omega 3. So, that we have some form of the PDE. If both A and B vanish, then there is no PDE, right, the LHS is 0. Therefore, we require that at least one of this A and B is non-zero at every point of omega 3. So, what is Cauchy problem? Here we are given a space curve gamma, which is typically given in a parametric version, where x component is given by Fs, y is Gs, z is Hs, as S varies in an interval in R, and the functions f, g, h are C1 functions on the interval. This is given. So, what is the Cauchy problem? It is to find a solution of the quasi-linear equation, but before that we need to assume something more, that is this projection gamma 2 of gamma of the space curve to R2 to the xy plane is a what is called a regular curve. What it means is f prime comma g prime is not 0 0 at each of the points of gamma 2, and we require that this z equal to Hs, right, that Hs must be given as u of xy, that is what we expect. So, u of Fs Gs, that should be equal to Hs. This is what we want to do, and as discussed before, we do not want S belonging to the entire interval I, but we are happy if we can find such a function with these properties where S belongs to a sub interval of I. That is, a part of the curve gamma lies on the surface z equal to uxy. Now, what are characteristic curves for linear and semilinear equations? They are the trajectories of the solutions of system of characteristic ODEs. In the linear case, dx by dt is A, dy by dt is B, dz by dt is of this form Cz plus D. In the case of semilinear equation, it is Cxyz, basically ABC, right, Aux plus Buy equal to right hand side, here also Aux plus Buy equal to the right hand side. So, these are the characteristic system of ODEs, their solutions and the images of the solution, they are the characteristic curves. System of characteristic ODE decouple into two sets of equations, that is what we need to observe. if it is a quasi-linear equation, we will have A of x by u, B of x by u and C of x by u. And because A and B do not depend on the third variable, the first two equations, if you look, they feature only x and y. Equation for x and y can be is given in terms of right hand sides, which are functions of x, y only. So, we do not require to solve this equation, we can solve these two independently. Similarly, in the semilinear equation, x and y can be solved for without bothering about the equation for z. So, it decouples into two sets of equation, a system of two equations for x and y which do not involve the variable z, we saw that, and a single equation for z which can be solved provided you give me what is x and y. Given a solution x t by t of the first two equations, we can solve for z. In other words, base characteristic curves can be determined directly without the knowledge of characteristic curves. Remember, characteristic curves are the tracer of the triple x t y t z t. As t varies, the trace of this is a characteristic curve, and when you project it to xy plane, you get x t comma y t as t varies. But here x t y t can be determined independent of z t. Therefore, we say base characteristic curves are determined directly without the knowledge of characteristic curves. This is possible since the equations for x and y do not involve the variable z. Otherwise, base characteristics are defined as the projections of the characteristic curves to omega 2. So, an idea to solve Cauchy problem for L and SL, we are dealing both L and SL together, mainly because the part where the first order derivatives appear is the same, AUX plus BUY. Okay. What is the step 1? Fill up omega 2 with base characteristics passing through gamma 2. So, what you do for this? Take a point x 0 y 0 in omega 2, pass a base characteristic curve through that point. How do you do that? It can be done. You have to solve this initial value problem. This is the equation for base characteristic curves, the first two equations dx by dt, dy by dt equal to a and b respectively, and you solve with this initial condition x 0 is x 0, y 0 is y 0. So, such solutions exist because we are assuming a, b are C1 functions. So, they are locally Lipschitz, this is an initial value problem and it has a unique solution which defined on some interval containing 0, all that is there. Therefore, there is a base characteristic through any given point x 0 y 0. Now, the question is, we are worried about gamma 2, that is where the data is given. So, question is, will it pass through a point of gamma 2? That is the question we ask, and because that is where the data is given, right, we need to solve Cauchy problem. So, that is why we ask this question. It will be clear in the next slides why we are asking this question. On the other hand, we can do one more thing, take any point in gamma 2. Why you have to take in omega 2? Take on gamma 2, okay, and then pass a base characteristic curve through that. Yeah, it can be done, exactly same procedure. You need to solve this initial value problem where x 0 y 0 there is replaced by FSGS. Now, the question is, can we fill omega 2 with such curves by varying points on gamma 2? So, these are the two different points of view. So, questions from step 1 are the following, right. Take any point in omega 2, pass a base characteristic curve through it, will it pass through a point of gamma 2? One question. Second, take any point on gamma 2, pass a base characteristic curve through that point. Question is, can we fill omega 2 using such curves? Answers to the first question is may not pass through. Second question is may not be able to fill. Okay. For both questions, we do not seem to have outright positive answers. Both answers are having caution terms may not, may not. But what we want to do? We want to solve Cauchy problem. Therefore, what is more relevant to us is gamma 2. Therefore, we work with curves which are constructed in this 2. Okay. So, therefore, that is the reason why we are going to look at curves which are defined using this point 2 here. So, we take points on gamma 2, pass base characteristic curves and then try to find a solution. That is the approach we will take, because the initial data is given on gamma 2, x equal to fs, y equal to gs, that is gamma 2, z has to be hs is the datum curve. So, with this decision we are giving importance to solving PDE near gamma 2. Yeah, because near gamma 2, why we say? Because we may not be able to fill up entire omega 2 by using the curves that we get in as an answer to step 2. Okay, we may not be able to fill, that is the answer, right. So, we may not be able to fill, but definitely we will cover gamma 2. So, we should be happy with that to start with. So, anything similar to ODE initial value problems here? Yes, there are similarities. There also, when we solve dy by dx equal to f of x y and yx naught equal to y naught, that is initial value problem, the existence theorem says there is a solution near x equal to x naught. That is why it is called local existence theorem. Okay, so, it is similar to that. Now, what is the step 2? Solution is found along each base characteristic curve. What is that? We will explain. So, let x equal to xts and y equal to yts denote the base characteristic curves passing through a point fsgs in gamma 2. So, this is what we have obtained in step 1. Now, I am writing this in quotes, it means that it may not be very rigorous, but this is a feeling. Okay? When we prove theorems, everything is rigorous. So, a solution u can be determined along each of the base characteristics found in step 1. So, setting zts equal to u of xts yts, I look at what is the equation this zts satisfies, because what is this? U of xts yts means I take a base characteristic curve xts yts, okay, for a fixed s is fixed here, and then u of xts yts is there, I can consider. Now, that I call zts. This is actually u along the curve xts yts, that is what I am calling zts. So, equation for zts is given by, of course, you have to differentiate dz by dt equal to ux into dx by dt plus uy into dy by dt. But dx by dt and dy by dt, they are solutions of base characteristic curves, they will be a and b respectively. So, what you have here is aux plus buy, and that is equal to c if you use a solution to the PDE. Therefore, this is equal to c of, this is in the linear case, c of xts yts into z plus d of xts yts, and if it is semilinear equation, it is simply c of xts yts z. So, we got an equation, a ODE, for the solution along each base characteristic curve. So, the equation for z is a linear ODE for the linear PDE, and it is a nonlinear ODE for the semilinear PDE. Nonlinear because the dependence of C on z is not linear, that is all it says. Okay. So, for L, the equation for z was this, I am recalling the equations. It is a linear ODE with variable coefficients, because the coefficients depend on t. Here also this is a non-homogeneous, you can take this to the other side. What you have is dz by dt minus c of xts yts into z equal to d of xts yts. So, you have a right hand side term and you have a variable coefficients here. Now, zts can be determined for all t in j. Okay, what is j? J is the interval on which you have solved xts and yts. You have to remember that these equations for base characteristics were solved, so that the initial condition was fsgs. Therefore, this interval j actually depends on s. I do not want to confuse you at this moment, therefore, I am not writing that dependence, otherwise we have to write t belongs to js. We will see this in a forthcoming lecture, I will highlight that point. Okay. So, zts can be determined for all t in j such that z0 is hs. Why is that? Because linear ODEs have global solutions, while nonlinear ODEs have local solutions as a rule. Okay. Nonlinear ODEs having global solutions is exception. Linear ODEs will always have global solution. Global solution means wherever your coefficients are defined, in this case the coefficients are all defined whenever t belongs to j, therefore, there is a solution for t belongs to j. Now, let us comment same about the semilinear equation. This is the equation, this is a nonlinear equation. Therefore, ZTS may not be determined for all t in j. It means that you may have to look at a smaller intervals of j, subintervals of j where z will be defined. Again, linear ODEs have global solutions, nonlinear ODEs have local solutions as a rule. So, now the third step is what we have done so far. Step 1 we have determined XTS YTS, second step we have determined ZTS. Now, we need to relate ZTS and XTS YTS. We hope that ZTS is U of XTS YTS. So, that is what is to be done here in step 3. Define a candidate solution. At the end of steps 1 and 2, we have a family of characteristic curves which pass through points of gamma. Okay, the family is indexed by the point on gamma. For example, yes. So, first of all we solved like this, we had a gamma 2, we took a point and passed one characteristic curve through that, another point, maybe another characteristic, another character, like that. And after solving XTS YTS, now we also have ZTS. And what is the initial condition? At t equal to 0, it is HS. Therefore, we have the family of characteristic curves are now passing through points of gamma. Base characteristic curves are passing through the points of gamma 2 and they pass through the points of gamma. Each member of the family is described parametrically by 3 tupular functions XTS, YTS, ZTS, defined for t belonging to a subinterval of R. Thus, we seem to have a surface, it depends what your definition of surface is, but we seem to have a surface, let us be very vague here, described parametrically by 2 parameters t and s, right, XTS, YTS, ZTS, t and s are varying. So, what you hope to get is a surface. We know that ZTS was designed to be the value of this, that was the definition of ZTS is U of XTS YTS, where U is a solution to the PDE, U was not known. Okay. We thought there was a U and then ZTS we set as U of XTS YTS, then we got an equation for Z thinking that U is a solution to the PDE, we did all that. So, U still has to be retrieved, that is what we are saying here, define a candidate solution. The question now is how to express a surface described by 2 parameters t and s as the graph of a function U defined on some domain D. Of course, D will be a subset of omega 2 for obvious reasons, which is also a solution to the given PDE. So, how to catch hold of such a function whose graph will be equal to the parametric surface that we have got. So, note that a curve or a surface, this is very general thing. Note that a curve or a surface which is parametrically described using smooth functions need not be a regular or smooth curve or surface. So, it can deceive us. It may have a very good description in terms of S and T, but actually it is a bad surface. It may have singularities. We will see that in many examples that we are going to consider in this course. The question posed above will be answered not now, but in a forthcoming lecture in the more general setting of a quasi-linear equation. We will do that with full details. Now, we have done for linear and semilinear equations, we use base characteristics and then got characteristics, and then from there we had a 2 parameter surface, right, a surface that what we think is a surface described by 2 parameters. So, why not do the same thing here for quasi-linear? Therefore, we ask the same questions. While trying to solve Cauchy problem for linear and semilinear equations, In step 3 we obtained a parameterized surface at the end of the step 3. Recall that the parameterized surface was described using the parameters S and T. The parameter S runs through the datum curve, S is indexed by the datum curve, and for each fixed S, as T varies, where is the T varying? The point will vary on the characteristic curve that is passing through the point Fs, Gs, Hs. Therefore, the following two questions arise naturally. What are they? Does the parameterized surface correspond to an integral surface? In other words, the question is z equal to uxy where u is a solution to the PDE defined on some domain. If the answer is yes, okay, sometimes you may say that yes, it is possible. Now, the question is if the answer is yes, then how to determine such function? How to determine that solution which defines the integral surface? In fact, this question can be more general. I need not write integral surface. Does the parameterized surface correspond to surface z equal to uxy for some function u? Then I ask whether that function u is a solution to the PDE. Whenever we see z equal to uxy and u solves a PDE, such a surface is called integral surface. Now, we have an assertion here, integral surface may be constructed using the characteristic curves. That is the theorem. Let D be an open and connected subset of omega 2. Let u be a function defined on D, which is a C1 function. I am not saying it is a solution to the PDE or anything, it is just a solution, it is just a function, and consider this surface z equal to uxy. Then the following two statements are equivalent. What is that? First one, the surface is an integral surface of the equation QL. In other words, what this statement says is that u is a solution to quasi-linear equation QL. Second one, the surface S is a union of characteristic curves for QL. So, before we proceed to prove the result, we need to understand what this previous theorem is about and what it is not about. Theorem answers the following question. Given a surface, I give you a surface z equal to uxy which is defined by a function which is C1 function defined on some domain D. When is it an integral surface of QL? That is what the theorem answers. Theorem also suggests that an integral surface may be constructed using the family of characteristic curves. The small missing point is that u, how do you catch hold of a function u? That is where the twist lies. Let us prove 1 implies 2. What is 1? 1 is the surface is given to be an integral surface. I want to show that is union of characteristic curves. Therefore, what do you mean by this? Surface S is a union of characteristic curves for QL. What is the mathematical formulation of this? It means that S is a union of gamma p, as p varies in S, of course. Gamma p is a characteristic curve passing through p. ABC is in C1 of omega 3, they are smooth functions, C1 functions. Therefore, a unique characteristic passes through every point in omega 3. Since S is a subset of omega 3, we have S is a subset of this union. Okay. Take any point in S, that guy is going to belong to gamma p for some p. In fact, the same p, let p belongs to S, then gamma p passes through p. So, therefore, this is a very simple containment, this way of showing. So, what remains to prove is S contains this union. So, we want to show this. How do we show this? Take somebody on the LHS. How somebody on the LHS looks like? He looks like a gamma p for some p in S. So, let p belongs to S, take the gamma p. What is gamma p? It is a characteristic curve passing through p. Now, we want to show that gamma p is contained in S, it is on S. What is S? S is given by the third coordinate z is equal to u of the first two coordinates x and y, u of x y. So, we have to show that. But recall that gamma p is the trajectory of the solution x t y t z t to the characteristic system of ODEs satisfying the initial conditions. At t equal to 0, it passes through the point P. So, x0, y0, z0 is P and defined on an interval j. At this stage, we do not know how big the characteristic curve is, except that such a curve exists through P and nearby P. So, we would like to prove that the entire characteristic curve lies on the given integral surface S. That is, the third component is function of the first two components. So, zt is equal to u of x t y t. This holds for every t in j. We would like to show this. But this equation is meaningful if and only if this x t y t belongs to the domain of u. Okay, domain of u is already fixed, u is given to us, it is defined on a domain D. Therefore, it is meaningful only if x t y t belongs to D for every t in j. Whether it is true or false is a different issue. First, whether equation makes sense, what question we are asking, is it legitimate question or not. So, u is defined only on D, that is the reason. Therefore, entire characteristic curve through P may not lie on S. See, characteristic curves are coming by solving characteristic equations, whereas u is given to you. So, they do not talk to each other. Therefore, we cannot assert that the entire characteristic curve lies on S, because this may not make sense. What we can ask is, for whichever t for which x t y t belongs to the domain D, then does it hold? That is a good question. However, x0, y0 is in D, therefore, by continuity x t y t will be in D, and you can find a subinterval of j such that x t y t belongs to D. Fine. X t y t itself is defined on j, but at 0 you are in D, D is an open set, therefore, for some time t in some interval j dash, which is a subinterval of j, you will be in D. Thus, this equation is meaningful for all t in that subinterval j dash. Note that j dash could be equal to j, we are not denying that, but what we are saying is that we cannot assert that, we cannot assert that j dash equal to j, it can be equal. If you are not careful in observing these points 1 and 2, we would have proved that the entire characteristic curve lies on S. This is a place where one makes mistake, because we are not careful, because what we are going to do later is simply differentiate this. Equation itself may not make sense. If you ignore that, you simply differentiate, go through the procedure and show that yes, entire curve lies on S, which is not correct, it is false in general, you have to be very careful. Okay. So, we are going to show that a part of the characteristic curve gamma p lies on S, that is zt equal to u x t y t holds for t belongs to j dash. Fine. So, define this function, this very much makes sense for t in j dash, because j dash was chosen such that x t y t is guaranteed to be in D, which is the domain of u. So, this is a good function, it makes sense. What we want to show is this function is 0. What is the usual strategy? Show that the derivative is 0 and at some point it is 0, therefore, it is identically equal to 0. If a function f dash is 0 and f at some point is 0, f will be 0, because f dash is 0 means f is constant. But we are not that much lucky, but we can still show that v is identically equal to 0. How do we show this? We show that v is going to satisfy a certain initial value problem for ODE, okay, and it is known, meaning that initial value problem which v is a solution to has only one solution. It is also known that 0 is a solution, therefore, Vt must be 0 solution. That is a strategy we are going to do. We will show that V is a solution to an initial value problem, we will construct or we will design that initial value problem, and the initial value problem has a unique solution and 0 is a solution to that. And the way we have constructed initial value problem shows that V is already a solution. We are also showing that 0 is a solution. Therefore, V must be identically equal to 0, and we have shown that zt equal to ux t y t holds for t in j dash, that means 1 implies 2 is done. So, how do we find that initial value problem? We want this to be a solution to that. Therefore, we start differentiating V and get that first order ODE. So, we will find a ODE satisfied by V simply by computing V dash. I am not going to these details, you have to use just chain rule. It is zt minus uxt yt. So, zt derivative is z dash t, this is ux and x dash, uy and y dash. But you know z dash is c, you know that x dash is a and y dash is b, and I want a ODE satisfied by Vt. So, right hand side also I would like to see Vt and anything else known functions which are xt, yt, zt, these are known functions, a, b, c are known functions. U is of course a known function. So, I write this like this. So, there is a V here and V here. So, it satisfies the equation u dash equal to FTU. I am going to write what is FTU. So, this is what I want to think as f of TV. What is that? It is going to be C xt yt u plus this u of xt yt minus this is a known function, I will keep it as it is. Wherever Vt is there I put a capital V or capital U, because the way I am going to write is in terms of U. So, this is the function. Recall that we are interested in applying Cauchy-Lipschitz-Picard's theorem and conclude that the V which we have defined to be identically equal to 0. We require the right hand side function f of tu to be Lipschitz with respect to u to apply Cauchy-Lipschitz-Picard's theorem. So, is f the function u going to f of tu, is it locally Lipschitz or not, that is very important. Indeed, there exists a delta positive such that f is continuous on j prime cross minus delta comma delta. So, the right hand side is continuous function and u going to f of tu is locally Lipschitz continuous in the variable u, that is what we need for applying Cauchy-Lipschitz-Picard's theorem uniformly with respect to t in j dash. And this follows from the smoothness of the ABC are C1 of omega 3 and u itself is a C1 function and p is a point in omega 3. Because of that we get such a existence of such a delta, and I leave it for you to fill in the details. V has the property that V0 is 0, we know that. What is V0? Z0 minus u x0 y0. Z0 is Hs, x0 y0 is Fs Gs. So, P is in S, therefore, it is true. Thus, we are led to the initial condition for the above ODE, that is u of 0 equal to 0. So, this is the initial value problem. U dash is FTU where F was described there and u0 is 0. This has a unique solution because f we have shown it is locally Lipschitz, therefore, this initial value problem will have unique solution. 0 function solves, very obvious, you have to check that 0 dash derivative of 0 is 0, therefore, it is enough to check f of t comma 0 is 0, which is verified here. F of t 0, you have to substitute for u is 0, you get this and that is 0. Since u solves Quasilinear equation, we are using that because statement 1 is given that u is a solution. That is it. So, this shows 1 implies 2. Now, we go to 2 implies 1. So, we assume that the surface is a union of characteristic curves and we want to show that this u is a solution to Quasilinear equation. So, let us proceed to prove that u solves QL. So, take a point x y in D and let P denote this point x y u of x y, that will be on S. Function u satisfies QL if and only if this equation is satisfied, ux uy minus 1 dot ap bp cp is 0, this holds. Since S is a union of characteristic curves and P is in S, it follows that there is a characteristic curve gamma P passing through P, gamma P is contained in S. Since normal to the surface S at the point P is in this direction ux uy minus 1, z equal to u of x y, ux uy minus 1 will be a normal direction, and a b c at the point x y u x y is direction of tangent to gamma p at p, therefore, their dot product must be 0. So, this shows 2 implies 1. So, this is a picture as usual this red x axis, green y axis, blue z axis. We saw this earlier, u x y equal to sin y is a solution to the equation u x equal to 0. Integral surface is blue, it is a union of characteristic curves are straight lines, we saw that already. They were obtained as intersection of two surfaces. So, datum curve is in magenta. So, this is the datum curve. So, that is 0 s sin s as s varies, that is the datum curve, correct. Let us summarize what we did. We attempted solving Cauchy problems L and QL. We were stuck where we had to find that function, we stopped there. So, we identified some point that require careful attention there, and then we understood the connection between integral surface for a quasi-linear equation and corresponding characteristic curves. We hope that this understanding will help us in solving Cauchy problem for quasi-linear equation. Thank you.